Hello everyone, nice to see you again. I hope you can hear me clear, right? And we will start today's lectures on modeling mechanical systems. Okay. Right. Okay. So as you have seen previously, we try to do some basic how would I say mathematical backgrounds on doing a Laplace transform and so on, right? So as you know, Laplace transform is useful, okay, when we deal with differential equations. Okay, so today we will go into how we can model it. Okay, I believe you may have learned this also previously. All right, so the goal of the day is you should be able to model a mechanical system into what we call a transfer function. Okay, so in this course, control engineering, the transfer function is an important block. Okay, that's you help us to analyze, okay, in the later part of the system course, okay, whether the system is stable or not, okay, how it will behave, okay, when we try to combine different type of I would say blocks or parts, okay, in between them, right? So here we would look into several basic mechanical systems. Okay, as you know, okay, in a basic mechanical system it consists of mass, spring and damper, right? So we will see that how we can model for 1 degree of freedoms translational part. Okay, the translational part which you have the mass, okay, absorber as a damper and a spring, all right, okay, to act in a 1 dimension 1 degree of freedoms systems. Okay, then also we would see that later on how we can use the basic, okay, the combinations of them, right, to actually uh, use it for 2 dimensional, right? You may combine it with different parts, okay, of mass spring damper system, okay, to create maybe multiple movement, right? Later on we will look into a rotational, okay, which is again a very important type of movement, okay, in mechanical, whether it's linearly translate, okay, or rotate. Okay, these are the two basic movement that we intend to produce, okay, in order to do any task, okay, of a system. Then later part we will just briefly go into the basic electrical system, as well as how we can visualize, okay, a combinations of electro and mechanical system together. Okay, so as we can see in a mechanical system itself, okay, it basically can be modeled using 3 basic components. Okay, here I mean in the translational type of mechanical systems. Okay, we would have a mass, a spring and a damper, right? So basically we can model many type of mechanical system using these 3 main component. Okay, it may or may not be in a form of spring or damper, but they are behaving, okay, in a similar form of spring and damper. Okay, right? So we can we can model the spring, okay, using the basic relationship that we know. Okay, we know that F equals to kx, right? But in this form we would write it in a kxt. Okay, meaning to say this x is a functions of time. Okay, we would change according to the time Okay, yeah, it will change according to time, right? So this is how we would want to model our system to know how it would behave throughout a time period of. Then also we have a damper, okay, which we could form a relationship between the force and the displacement itself, given by the force equals to the damper constant Fv and the velocity. Okay, so this represent a velocity, right? Dx over dt is a velocity, right? Okay, and also the final part would be the inertia. The inertial part is referring to our object. So what this object actually does is it has an inertia, right? So that inertia will continuously move, okay, as long as we don't stop it, or it will continuously stop, okay, if we don't move it. Okay, so this is the idea behind it. So we can relate them between if you want to accelerate or move a mass, okay, it must accelerate. Okay, so the mass must accelerate when we give it with a force. Okay, so we have the F equals to m accelerations. This is the accelerations term, dx square over dt square, right? So to simplify this one, right, since the control book that we applied there is mainly on, I would say, electrical, okay, more on the electrical part, okay, but nevertheless, okay, it's still useful that they call this term as impedance. Okay, so impedance is referring to a value where it's equals to the f divided by the x. Okay, so if we bring these terms over, then we will see so-called a constant or impedance to represent a spring. Okay, we will go through this concept later on, okay, how we can apply this. Whereas for the viscous damper, okay, if we bring out the x, then we would have a FVS. Okay, if we for a mass, then we have ms square, okay, which is referring to the double differentiations of the x itself. Okay, so first we will just go back to the basic, right? How it can how we can form the equations of motion. So this equation of motions is important, okay, in mechanicals to describe a motion, how it's behaving, okay, by when it is subjected to different kind of forces. Okay, so when we try to do with equations of motions, the important part is we should able to isolate the object, okay, so that we can analyze the kind of forces acting on the object or the mass itself, okay, in order for us to derive, okay, how this object actually move. Okay, so if we have multiple objects that are connected, then we can analyze each of these objects separately, right? So that is the idea of free body diagram, okay, that you have learned previously, an important concept, okay, that we would apply throughout the course, okay, throughout your 4 years, right? So the idea is that we separate or isolate the system itself to describe the motions of our interested mass or object. Alright, so here obviously we have only one object, the mass, the m itself. Okay, so we want to see how this object actually behave under different kind of forces, okay, that being connected to it, right? So here, if we separate it during an equilibrium, meaning to say when the mass, this m itself doesn't move, then it should be not moving, okay, and when it is not moving, meaning to say the force is in equilibrium, the amount of force acting on the object is equals to the force against that kind of motions, right? So here the basic forces that connected to this mass would be the weight itself, the mg, and the the force due to the spring. Okay, so you can see that the mass is actually rests on a spring, the K itself, right? So you have the K here, okay, to support the weight of this mass. Okay, so eventually when you put on a weight, a mass on this spring, okay, so this spring will now being compressed, okay, to a certain distance. Okay, we call it as x naught. Okay, the initial compression, so we denote as x naught. Okay, so this x naught will represent the equilibrium force that being exerted by the spring on the mass, right? So this is the equilibrium, so we can write in equilibrium the weight minus the force given by the spring equals to 0, no movement, right? So now since we are interested with the motions, okay, how it would behave when the object is moving, then we would try to introduce different kind of relationships, okay, in the object. Now we would want to see, okay, beside the weight, the mg, and the inertial spring compressions, okay, what are the forces that actually exert on it, right? So now we would try to establish some sense of direction. So here we may, okay, up to you, okay, it doesn't matter, okay, you may want to express it downward as a positive, so that's why I just highlight xt downwards as a positive direction. So whenever it moves upwards means negative, you may always reverse the directions as well, okay? So once you have these directions, also you would want to see the directions of the accelerations of this mass, okay, should be consistent with this positions directions, the xt. So if we assign downwards as positive, then the mx double prime, okay, the ma itself should also moving in the same direction downwards as positive, okay? Whenever it accelerates upwards, then you will get a negative value, that's all, okay? So the directions must be consistent, that's all, okay? It doesn't matter whether you want to assign upwards as positive or downwards as positive, okay? Then once you have these directions, okay, then we would now check in this free body diagram, the m, okay, what are the forces that actually act on it, okay? So we can see that when we isolate this mass, then you will reveal that there are actually 4 additional forces, okay, that are exerted by the spring, okay? Not only the initial one, if it is continuously being compressed, okay, when the x is being moved, then you will have an additional force being exerted by the spring in the upwards directions. Therefore we would write a kxt, okay, which is fluctuating according to time, right? Then also when we isolate the damper effect, then this damper effect will give us the fx or the fv, okay, fx prime or the fv, okay? So this is the damper effect in terms of force, okay, towards the motions, okay? So this damper directions will always how would I say, it will always make or always against the directions of the motion. So if the mass is going downwards, it will always against it, okay? If the mass is moving upwards, then it will pull it back, okay? It will delay the motions of the mass. That is the functions of a damper, right? Then we have established all these connections of force. Then also we may want to know if we give an external force to your object, right, then how it would behave. So we would like to also include an external force, okay, F external, okay, in the time, right? So this is where if we know the relationship between the external force and this mass spring damper system, then we would able to control the motions of this mass, okay, by controlling the force, okay, given into the system itself, right? So now based on this diagram, right, we would use the Newton's second law of motions, okay, to form our whole equations of motion. So the idea is that the summations of forces acting on the mass should be equals to ma, right? That's all. Okay, so we will see that in this left hand side of the equations is the summations of all the forces acting on the mass itself, okay, during the motion. So we have the minus Fv, remember downwards is positive, we define that, so upwards is negative. Then we have kxt negative, the kx0 negative, okay, then plus the F external and the mg, right, equals to the ma, alright, the based on the Newton's second law of motions, right? So this is how we can write the equations of motion, right? So now we will see that this during equilibrium, okay, these terms are actually equals to 0. mg minus kx0 equals to 0. So if we group these two together, we can remove them together, remove them out, because this equals to 0, okay? So eventually our equations of motions now is general equations that consists of mx double prime plus fvx prime plus kxt equals to our external force. So these equations you will see it in maybe in a different notations, okay, throughout this 2 or 3 years course in mechanical engineering, okay. This is the basic equations of motions, okay, the general equations of motion that you can derive, right? Now once we have this, our task, okay, in this course is to use this and form transfer functions, right? So in these transfer functions, now we can see that the equations of motions, okay, the equations of motions here where is my mouse? Okay. So in these equations of motions now, what we can do is we want to turn it into a Laplace form, okay, the S domain. So you just do what you have learned, okay, in mathematics, okay. So this is the equations of motion. Take a Laplace transform, you would see that this x double prime become s2x, okay, this x prime becomes sx, okay, and this xt become xs, right? Okay, so if we bring all this xs out, okay, you would reveal this common form, okay. You have ms square plus fvs plus k, right, equals to the external. So this is the Laplace transform form, okay, and when we assume a zero inertial conditions, right? So if we now try to solve this out, okay, in the transfer function we would always want to express in this way, okay. What is the output or our displacement in our mechanical system itself, okay, the xs, okay, when an external force is being applied, okay, so that the external force now will become our input. So we have xs over f external, so we will now get our transfer function as stated here, right? Now back to the impedance part, okay. If we are familiar with the impedance, we know K impedance is K, Okay, for the spring, the impedance is K. Viscous damper, the impedance is FVS. Okay, for the mass is ms squared. Alright, so if we know this one, now we can directly form the transfer functions much faster. Okay, we don't need you to actually go through the derivations of from the force x and so on. All right, so what we need you to do is you would able to draw the free body diagram, and from that free body diagram you identify what is the component and the corresponding impedance that you may use. Okay, so here we just based on the free body diagram during the motions itself. All right, so during the motions, now we remove the parts where there is mg and there is the kx0, right? So during equilibrium, those forces we remove out. Okay, so now only remain those involved during the motions, right? So during the motions, now you can see we have fs, we have k, we have the fv. This fs is the external force. Okay, so this fs is the external force. We have the spring force, we have the damper force, and now remember in the second Newton law we have the accelerations, okay, ma terms, right? But here, okay, in the impedance, now we would want to use the terms called inertia, right? So the mass itself, due to the mass, okay, it would have the effect of inertia. Okay, so this inertia is being denoted as ms square. So this inertia again is something similar to a damper. Okay, because if the object is moving, so in order to stop it, okay, it will delay the stopping, so it will somehow against the force, okay, being given to the system, right? So that's why if the mass is moving downwards here, okay, in our this free body diagram, right, then the inertia now it will try to against these motions, okay, because it will try to delay the start. Okay, if it is not moving, now you start to press it, right, then this inertia will delay the kind of effect of this force, right? So that's why this ms we would write it in opposite directions, okay, of the movement itself. Now you will see this this free body diagram, okay, but you would also notice that now we write it in impedance form. Okay, we don't write kx f v and so on, right? So we just write the impedance. So for the spring we will write k, the mass, the inertia, the ms square, the fvs, and the external force. Okay, so once we have this one, we can now rewrite the equations. Okay, the summations of all this impedance should be equals. Okay, so you can see that up equals to the down, right? So that is how we can now form the same transfer functions. Okay, this form is exactly the same with the previous one, right? Only this one, maybe the notation I write f external, that's all, right? So it's exactly the same, and you would get the same transfer function. This is the idea using the impedance, right? Next, how we would now use this single degree of freedoms derivations method to a multi degree of freedom system. Okay, now we just look into a two-dimensional 2 degree of freedoms system. Okay, when we involve two mass moving, all right, so two mass moving, then each mass will now have a freedom to move. Okay, so that's why if we have two mass, So we have 2 degree of freedom, so they will move according to different patterns that they would like, okay, according to the law of physics lah, right, for sure. Okay, so how we would now translate these systems, okay, these 2 DOF systems into a transfer functions, okay. We just quickly go through these ideas, okay. So if we have a mass, okay, sliding on a floor, right, so this floor actually there is frictions, okay. As I mentioned, all these mechanical systems you can always translate different kind of forces acting on the system that behave similar to the either mass, spring, or damper, right. So this friction itself actually act similar to a damper, okay. It will always act against the movement of your mass, okay. So if it move this way, so it will always give a force, okay, to against it. If we move backward, okay, then it will change directions, okay. This is the behavior of the friction, so it's similar to a damper. That's why we just put FV1, okay. Then also we have a damper, a spring here, okay. We have a spring here, spring here, so we just put a notations 1 1 1, okay, 2 2 3, okay, 2 1 2 3 3, okay. So just being consistent, okay, how you want to assign all this numbering of the constant, okay. That's all, okay. So now how we would form these transfer functions. When we start to form the transfer functions, we must again isolate the system, right. So here we will start with the M1, the mass 1 itself, okay. So if we try to isolate this mass 1 only, right, so then we will cut through the spring 1 and spring 2 as well as damper 3, okay. Then also we have the actions of the frictions at the ground, right. So we just translate this into all the impedance, right. So assuming now the positive direction is on towards the right as positive, right, and there is an external force, you can see that in this whole diagram itself, okay, there is a force acting only on mass 1, okay. You can see that M2 there is no external force, so you have to be careful with this, okay. So where is the external force being act, right, on which part, right. So now we have this Ft here, right. So what we do, we isolate this system using a free body diagram concept, okay, and also we use impedance to extract our derivations, okay, into a transfer functions. So we have M1, positive direction is x1, okay, then external force F2, Fs, sorry, okay, to the right positive directions, okay. Then the rest now we will start to identify. When we cut through a spring, okay, when we pull a spring, what the spring will do, it will pull back, right. So here the spring would have this K1 X1, okay, because all these motions is related to mass number 1, so it's related to X1 movement, right. So we only analyze when M2 is not moving, okay. Now we have to isolate also another movement, or that this M1 will react, okay. We assume M2 is not moving and M1 now move to the right, okay. So because of that, this M2 now is acting just like a wall, right, because it's not moving, okay. And because of that also, we can write this is K1 X1, okay. Then we cut through over here, then the second spring, when we push to the right, then this spring will now push back also, right. So we have these directions, of the spring 2. Okay, then for the frictions, for the frictions, when the object moving to the right, then you will give a force against the object movement direction, so we Fs. Okay, also we have what else? Okay, this damper, so when we cut it through, it acts in a similar form, right? So Fv3. And finally, don't forget your inertia, okay, the mass itself. So if the mass is moving to the right, so again the inertia will act against it. Okay, so you have this m1s2, right? So this is how you can form your first part of the transfer functions. All right, not really the full transfer functions. Okay, so next we will see the effect, all right, when m2 is moving. Okay, remember the previous one, m1 is moving but m2 is not moving, so m2 is acting like a wall, right? But now we would also want to see, okay, what if m1 is not moving, okay, m2 is moving, okay, how this m2 movement will affect this m1, right? So we want to know what is the additional forces given by another moving object, which is the m2. Okay, so here our focus still m1, okay, but this m1 doesn't move, m2 is moving, right? So here m1 is fixed, m2 is moved. Again, directions m2 to the right is positive, right? So when this m2 is moving, what happens is that m1 doesn't move, so k1, the forces exerted by k1 is negligible, right? Not moving. Okay, only the frictions also become 0 because it's not moving. Okay, the only part or component that will have a force acting on m1 because of m2 is moving is the spring number 2 and the damper number 3. Okay, so this spring number 2, when m2 is moving, okay, when this spring move or m2 is moving, so what happens is that this m2 move and it pull the m1 through the spring. Okay, so that's why you will see that this spring k2, the force is going along the directions of m2, right? So you will see that at k2 is have a directions towards the right hand side. Okay, and now we will also write this x2. This is because of the movement of mass 2, right? Remember previously, all this is because of the movement of mass number 1, right? Whereas now we only consider movement of mass 2. Okay, so we have this k, the force due to the spring number 2. Besides that, there is also a movement of the movement of m2 also affect or give a force, okay, through the damper itself. Okay, so again the directions is along the directions of the m2 pull, okay, no matter what it is, okay, it move on that side, even though it's damper, so this damper also move, okay, but it may be in the lower speed or response, okay, but it still move to the directions of m2. That's why the fv3s also move to the right, okay, due to the effect of x, the mass 2. Okay, so this is the idea when we form this one, right? So we can now see that m1, okay, may respond to two things. Okay, first, the force acting on to m1 itself, and also the second part would be the action due to the movement of other other object, the M2 in this case. Okay, so how we would want to combine them, okay, in the two-dimensional system is we do a superimpose, okay, of these two system itself. Okay, one is due to the movement of x1, the other one is the x2. Okay, we combine them everything into one single block. Okay, then we would now see that x1, okay, so we can have k1 plus k2, these two grouped together. Then also this fv1s, fv3s, we can group them together. Okay, sorry, this is a small f, right? Then the inertia of mass 1, okay, the external force F, okay, then this forces, okay, due to the movement of M2. Okay, so you can see that M2, the moment of the mass inertia of M2 is not reflected here because this free body diagram is only about M1. M2 mass is not there. Okay, it's only moving but and giving a force, okay, effect to the M1. That's why M2 is not there. Okay, M2s2 square is not here. Okay, because we're only interested with M1, right? So once we do this superimpose or superpositions of all these forces acting on it, we just do the usual thing. Okay, summations of all these things equals to the external force, right? So we just group them into x1 and x2. Okay, we separate these two motions, x1, x2. Right? So now the question is, in order to express the transfer functions, okay, maybe in this case we want to see the relationship between the force input, we apply a force, and what or how it would affect the F2, okay, the movement of the x2, the movement of the mass number 2. Can we describe this? Is it sufficient using these equations? We will see that x1 and x2 is two I would say two unknown or two variables that are moving, right? So once we have these two variables moving, is it sufficient using one equation to actually describe the whole things? It is not possible, right? Okay, so that's why now we have to do the second part, right, which is the same free body diagram methods and so on the M2, right? So this would be the superpositions one. Okay, you may try to practice this one, okay, for M2 on your own, right? So eventually based on this one, you would get the second equations, right? The second equations over here. So once we have this second equations over here, now is it sufficient? Two equations, two unknown. Now based on what you have learned, right, simultaneous equation, it would be sufficient, right? Okay, regardless of this is x1 or x2, okay, you still need two because you want to solve one of these, right? So assuming this is what we want, the x2 is the output that we want to investigate, so we combine them together, right? So we combine them together, we solve it using simultaneous equation. You can substitute this x into this this x1 into this x1, rearrange it, right, and solve it, right? Just a matter of time and patience, okay, to write all these notations 1, 2, k1, k2 properly, okay, then you should be able to solve it, right? So just be careful with all these things, right? That's all. Okay, so if you want to solve it in a more systematic way or easier to visualize way, okay, you can always use a matrix form. Okay, you group them into a matrix, right? So x1 here, right? x2 is here. Okay, so first equations we would have this part over here, x2 part, don't forget this negative, all right, over here. Then we have this part until, okay, here, this part, okay, this part over here, right, and then this part over here. Okay, so if we form into a matrix, okay, so we would read in this way. Okay, this multiplied by this plus this multiplied by this give us the second one, right? So which is equivalent to our equation B. All right. Okay, so based on this one, in the matrix form, now we can use the Cramer rules to solve it. Okay, so if we want to get the solutions of x2, we want to know what is x2. Okay, what we need to do is, if we want to know x2 means it related to the second column, right? So the second column part, okay, what we do is we use this part, substitute into second column. Okay, so it form this, okay, f, s and 0, right? Whereas this first column remains. Okay, so we do a so-called modulus of it. Modulus of it means this multiplied by this minus this multiplied by this, right? So we get this, right? So this would be our upper part. Okay, divide by the bottom part, which is the modulus of this matrix. Okay, so this multiplied by this plus this multiplied by this. Okay, so you just do the arithmetic. All right. Okay, and finally that would give us the solutions, okay, of x2. But we, in our transfer function, we want to divide them with the input, right, the f. Okay, so that's why we multiply by 1 over fs, right? This is the idea behind it, right? So eventually you can able to form these transfer functions. Okay, it looks very complicated, right? It looks very complicated with a lot of alphabet here and there, right? But when you practice, okay, just use practice. Okay, you try to write all these numbers in and so on, then eventually you will reduce all this alphabet and turn them into numbers. Okay, it's basically it's just a numbers at the end, right? That is the main concept of the transfer functions, okay, being derived using impedance, a free body diagram for a translational system. Okay, so any questions so far? Okay, we will just take a just check, okay, if you have any questions. What is viscous damper? Okay, to answer this viscous damper, you know absorber. Absorber itself is acting like a, how would I say, any movement, okay, that's it will try to delay that kind of movement. Okay, if that is what it called as a damper. Okay, and the viscous part is referring to the characteristics of the damper itself. Okay, it become smooth. Okay, in the way of it damp the motions, right? So far said damper to slower the motions. Yes, it would so-called say yes, it slower the motions, the response of the motions, I would say. All right, so if you have an object, okay, if you are connected to a viscous damper, so when you pull, so this viscous damper will try to slow slow it down so that it move in a smoother way, okay, before it start to accelerate, right? Just like your car, when you hit a bump, okay, so your car will now, your car will not immediately down, right? It will slow it down before it accelerate faster, okay. That is the idea of damper. Okay, still little confused of Kramer rules. Okay, alright, so we just quickly go back to the Kramer rules for a while, okay, and maybe later on you may do some tutorials, okay, practice on your own to see further, right? Okay, so go back quickly to the Kramer rules, right? So the Kramer rules basically is to get the solutions, right? Maybe you can't see the form itself, okay. So the Kramer rules, once we apply a Kramer rules, we actually solving for S2, okay, okay, which is equals to these two part, right? Okay, so in the Kramer rules itself, the first part, the upper part, okay, of the solution is that if we want to solve for the x2, which is the second part, right, then you would use this second column, okay, which represent x2, right? This one represent x1, right? So always this one multiply by x1, this part multiply x2, right? So this part you use this term, you just replace it, right? Replace it here, so you will form this triangle y, okay, delta y, okay, in this modulus form, okay, of x1 column everything exactly the same, and this x2 column you replace it with your how to say, the right hand side terms, right? You take a modulus of it, okay. So when you take modulus, it's basically you do a cross multiplications, right? This plus this multiply by this give us 0, minus this multiply by f2, okay, so minus minus, so that's why we get this positive part, right? So once we get the upper part, okay, for the bottom part it's just the delta, okay, which is the modulus of the matrix that we have, okay. So again, the matrix of this is these multiplications, right? So eventually you get the x2, okay. So this is the Kramer rules to solve for one of the variables. If you intend to get x1, then you will have delta, let's say x, okay. This x is just a notation, right? And this x now, our intention is x1, so we would want to use this one, okay. So in this case, then our delta x would be equals to, we replace this column, okay, with the fs side, okay. So we have fs, okay, and then the 0, right? And the second part would be this whole terms right here, okay, and we find the modulus of it, okay. Bottom part remain the same, okay. So you get the solutions of x1, okay. So after we get this, in order for us to get the transfer functions, we have to divide, because we want the fs, right? So everything divide by fs, okay. So we get the answer, okay, or of the transfer functions. Okay, right, so now we would move on to the rotational mechanical systems, okay? The idea very similar to translational. So first you just practice on the translational, make full use of this, Then after that, the rotational is very similar. Okay, it's just instead of force we use torque. Okay, instead of x we use theta. That's it, right? We still have spring, viscous damper, but everything is in the rotational form. Okay, and your mass is rotating as well. Okay, so in that sense, the inertia is now the I or the J in here, the moment of inertia. Okay, and the angular accelerations, okay, of it. Okay, so the idea exactly the same with the translation, only the notations of force and torque, okay, and theta and x. Okay, that's it. So here again we would just go through one examples of it. Okay, how it looks like. Okay, we will not go through in details now. All right, so you have a shaft, right? So basically this shaft, it can be a same diameter, it can be in different diameter. Okay, it's up to your systems that you intend to solve, right? Because this shaft, okay, even though it is rotational, even though it's made of steel, okay, it will still twist. Okay, so remember, if this is a steel ruler, okay, assuming this is round, okay, what happens is that when you turn on one side, so this spring, this ruler actually twists. Okay, so this twisting actually act like a spring. Okay, this is a spring, so when I release it, go back to the original form. All right, so this is the effect of mechanical bars or rod. Okay, it have this effect of spring, okay, inside it. Okay, this effect will, if it is short, then this effect may be negligible, so called negligible. Okay, we don't need to use the spring to represent this long bar in between them. Okay, but if this is a very long shaft, okay, so this long shaft itself, now if one side maybe 10 meter apart, okay, so if one side is rotating, okay, the response rotate 1 degree, so this response of 1 degree will now being may or may not affect the other side because of this spring itself. Okay, that's why we will represent that there is a K inside these connections. Okay, assuming this is long, we don't know long or short. Okay, we just put a K to represent this behavior of the rod. Okay, then on the other hand, there is a bearing to support them. Okay, so there is a bearing here and another bearing over here. Okay, so this bearing again, it acts like frictions. Okay, so it acts like a damper. Okay, so when you start to rotate, you may need more force to rotate, okay, before the bearing actually getting smooth. Okay, and when it is rotating at a very smooth way, then now you will have a problem like to stop it, then you may, if it will now try to delay the stopping of it. Okay, that is the idea of the damper, right? So you have bearing D1 and D2 to be represented by a damper. Okay, so you can represent it with damper 1, damper 2. Okay, so you can see that we translate this mechanical system into mass, spring, and damper, right? So after that, the rest is similar. Okay, we would do the impedance way. Okay, but here instead of movement in x directions, we now consider the rotations, okay, in the positive direction. So let's say we take clockwise, yeah, clockwise as positive. Let's say we take clockwise as positive, so it should be consistent for mass 1 and mass 2. Okay, mass 1 and mass 2, clockwise is positive. Right, so remember this, I purposely do this in 2 different diameter, okay, so that you can visualize that they looks like a different different object, okay, but eventually it can be a same object, right, with the same diameter. That's it. Okay, so we just want to see how it will respond on one side towards the other side. All right, so here you have the one of this segment. We have this part, right, rotating. Okay, and because of these rotations we have also a torque, okay, acting on the J1 side. Okay, so torque acting on J1 side. Okay, so torque acting on J1 side. Then damper will delay the movement of this rotation, so you have a damper D1S. Okay, and also the moment of inertia that delay the accelerations of the J1. Okay, so you have the inertia comes over here. Okay, same thing for the spring. Okay, remember this is a so-called 2 DOF systems. Okay, so assuming this one not moving, okay, this one moving, so K1 will the spring K will also give against the movement of this torque, okay, or the rotation itself. Okay, so eventually this is how it looks like. Okay, then now when the J1 is not moving, okay, now we take J1 not moving, only J2 move. Okay, so when J2 rotate in this way, now it would turn the spring also rotates along with the directions of J2. That's why J2 rotates in a clockwise direction, so the effect of J2 I just put in the red color here. Okay, J2 over here, right, rotating along the directions of the clockwise directions. All right, so eventually we have a superimposed free body diagram over here, okay, to represent the J1. Same thing with the J2 part. Okay, J2 part we have the effect when J2 is moving, J1 is not moving, represented by the black color. Alright, and when J2 is not moving but J1 is moving, okay, then we have the green color. Right, this is the graphical representations of how they are affecting, okay, on the J1 and J2. Right, so once we have this, okay, we can always write for each of these, we superimpose all these effect into one equations, the other on the second equations. Okay, we just go through one of it. Right, so one of these, okay, we have theta 1, theta 1, theta 1. Okay, so theta 1 would consist of J1S2, okay, and D1S, okay, and also K. Right, so all of this is on the same directions. Right, same negative direction, so let's say here is negative. Right, then we have also K theta 2, okay, on the opposite directions. Okay, so assuming this is plus, right, and this one is plus TS, okay, equals to 0. So when we rearrange, that's why you will get this form. Alright, the same thing you can do for the second equations. Okay, use Cramer rules, solve it, you would get the transfer functions. Okay, the transfer function not necessarily theta 2, okay, it can be theta 1, theta 2, depends on what is the output that you are interested with. Okay, you may want to know how it will respond, the theta 2 respond to the top, okay, or you may want to know what is the response or angular displacement of J1, okay, when we apply with the torque. Okay, that is being represented by the transfer functions. So once we get that idea clear, then we would also want to know how the gear, okay, which always a mating pair of gears, okay, affect the equations of motions or the transfer functions, right? So in the mechanical systems, there is a lot of gears, okay, and all these gears itself also is a mass, okay, which consists of J1, okay, J1, J2, and so on, okay. So they may delay, or you may need additional torque, okay, to accelerate them to the desired velocity or accelerations, okay. That's why we would want to model them as well, okay, how it would react, okay, when we have these combinations of gears, okay. So we would represent them like this, okay. This is gear 1, gear 2 connected to second part, right? Okay, so and the relationships are given as such, okay. This relationship is related to the displacement at this particular point, r1 theta 1 should equals to the r2 theta 2, the movement of this point itself, right? Then also the torque theta should be equals, okay, for each of this gear system, right? So from there you can relate it with the number of gears, okay. N1 N2 is the number of teeth, okay, number of teeth, okay, which is easier representations of, instead of counting the diameter, it would be easier to count how many number of teeth, okay, of a gear itself, right? So this is the relationship between them, right, with respect to the number of teeth, right? So now we will see how it actually affect, okay, or in other terms that they usually use, okay, they call it being reflected, okay, on the other side. So you have one systems, okay, you may want to see how it's being reflected, the effect of all these gears, okay, being reflected to the domain or the variable that you are interested with, right? So here let's say we are interested with the theta 1, okay. We would want to know theta 1 and t1, how it would behave, okay, because this is our motor, okay. We would want to know when this motor connected at this point, okay, giving a torque of t1, okay, how the accelerations of this theta 1 will change, okay, on this particular system, okay. So now we would want to reflect all these components or system of motions, mass, inertia, okay, towards the input, okay, the theta 1, right? So theta 1 and t1, okay. So this is the idea of it, alright, how we can reflect all these things into the part that we intend to check, okay, so that we can later on control properly, okay, by putting the correct torque, okay, on the motor. Then it will give us the suitable response to the output, okay, of this rotating part, okay. So now we just have this simple representations through one pair of gear, right, a pair of gears over here. So we just represent the pair of gears here with a number of teeth 1, N1 and N2, right, and it is connected to this rotational system, okay, that we have gone through previously, right? So assuming this is the rotational systems that we have, okay, we can describe these rotational systems over here as J2 square, okay, plus ds plus k theta 2 equals to this torque T2, right? So this is the equations of motions to represent this part. Right? Okay, so now we want to know how this part will affect the theta 1 and T1, right? How it would behave, okay, when we reflect all these things into there. So what we would do now, based on the relationships, we know that T1 and T2 have a relationship, okay? Just go back, okay? We can see that previously the T1 and T2 have this relationship, okay, whereas the theta 1 and theta 2 have this relationship, okay, they are inverse, okay, whereas for the T they are proportional, T1 and 1, T2 and 2, right? So based on that, okay, so T2 now, okay, we can translate or change or convert them into T1, okay, by having this ratio, okay. So remember, T2 divided by T1 equals to N2 divided by N1, right? So we just move over, multiply, so we should get this form, right? Then same with the theta 2, okay, we just translate, okay, so we have this form, right? So once we have this form, now this N1, N2, we group them together, okay, so this one move back here, okay, so move back here, then eventually we get N1 divided by N2 square, right? And now the rest of the equations will have the parameter being reflected at point 1, okay, which is theta 1 and T1, right? So we can see that through this pairing of gear, okay, then it would give us an effect of the gear ratio, okay, the ratio between them, okay, square it, right? That is the main idea of it, right? So you can see it being reflected through this ratio, okay, which is a power of 2 ratio. Okay, here is an examples, okay, how now it being connected through one pair and the second pair of gears, okay. So this is a shaft connecting them together, right? So there is a bearing here, so there is a D1 here, okay, there is one single bearing over here, so there is D2 but no D3, let's say, right? And this is connected here, so no bearing required, let's say, right? So you can always represent this in this form, right? So in order to get the transfer functions of this, okay, you just have to reflect from this point to the second part, all right? So now what we need to do is we would translate this whole rotational gearing system into this general forms of equivalent system, okay, which only consists of the J equivalent and the damper equivalent, okay. So this is the main idea, right? So how we would do that, okay, we would just make a quick shortcut here, right? We know that it's being reflected and we have a ratio of the gear ratio square, okay. So what we would do now is that if you intend to know what is the mass moment of inertia at J1, okay, J1 itself, since it's connected to J1, the J1 will not need to have this effect of ratio, okay. But when this J2 and J3, okay, they are connected at the same they are connected to the same shaft, okay. So therefore you can see that they are rotating at the same shaft, so you combine this J2 and J3 together, right? So J2 and J3 together with a gear ratios of N1 over N2 square, right? Because they just connected to the one tier, okay, just next to it, right? Then for the third part, okay, which represent this load, okay, and the J4, okay, which is another one rotational system, okay, so they will rotate together here, okay. So this J4 and JL, right? Yeah, this should be JL, okay. So this now would have two tiers of pairing, okay. So there is a N3, N4, and one pair of gears ratio, and the second one and this N1 and N2, okay. So what you need to do is just multiply this ratio together, right? So this N1, N2, and then N3, N4, right? N3 over N4, so square them, right? So you would have this simplified reflected mass moment of inertia as JE here, okay. So same thing with the damper, you just have to identify damper 2, since damper 2 only one tier, alright, of tier pairing, so only one side, okay, the rest nothing here, right? So once we have this equivalent JE and DE, okay, so you just put it back, okay. So we now have this simplified or equivalent systems of this rotational gearing system, right? Then you can easily represent them in this form. Okay, so once we have that two clear part, okay, the mechanical system of translational and rotational part solved, okay, the rest now is become very simple, right? So we also can match them in the electrical systems that you have learned before, okay. So force is actually equal, similar analogous to the wattage and so on, right? Same thing for electrical network, you have this impedance, okay, you have the capacitor, resistance, and inductance, which will form electrical networks, okay, three linear components of it, okay, being represented by this impedance, okay. So this impedance is respect to the current, right? And if we want to analyze a circuit, okay, then we also have this capacitor, resistors, inductance, resistors, and the capacitor itself, okay. So if you intend to know how the voltage actually change across this capacitor, we see, okay, when the voltage is applied over here, right? So we can use the same methods, okay, analyze them using the impedance, okay. In this so-called loop itself, there is the inductance, okay, which can be represented by the Ls, okay, then the resistance, the R, and the capacitor 1 over Cs. Is it correct? Yeah, 1 over Cs, okay, 1 over Cs here, okay. So just group them together, multiply by the current, okay, since you can see that this is over I, okay, this is over I, right? So we multiply by I over here. When we move it over here, this will be V over I, right? So this is the ideas behind it, right? And also, if we intend to now, instead of current, we want it to be in the voltage form, VC, okay. So we also know that V and I relationship is given as such, okay. So once we know this relationship, we just substitute it in, okay, then we would form these transfer functions, right? So in these transfer functions, you can see that we later on, okay, most of the books, they intend to write in the form of fractions 1 over certain parameters, okay, because our idea is to bring this highest order, the S domain, okay, with a constant of 1. Okay, so if in order to remove this LC, so we just divide by LC everywhere, okay, including the upper part. So we can see that the bottom form of these transfer functions will now in the form of 1s square and so on. Okay, so this is the main idea of why they divide by LC and so on. All right, and after that we can always, once we get these transfer functions, our first task done. Okay, we can represent them into a block. Okay, the block of transfer functions, the output and the input. Okay, the output is the VC and the input is V. Right, so this is the main idea of transfer functions, and after that we will represent them using a block diagram. Okay, so even in a motor, DC motor, we can represent with a so-called coiling, okay, of different resistors and so on, okay, that represent the characteristics or response of the motor itself. Okay, and the mechanical part which we intend to derive this whole sessions, right? So when they combine together, we will now have the control from the very upstream part, okay, the voltage part or the current part, okay, in order to control this mechanical system on the right hand side. Okay, so this is the idea of the block diagram, okay, which we will discuss further on in the next sessions. Okay, so today's part is to model it into a transfer functions. Next part we will look into how we would simplify combinations of block diagrams, okay, blocks, okay, into a simpler form in the next part, right? Simplifications of block diagrams. Okay, so I hope that's is clear for you for these sessions. Okay, how you can model mechanical systems into a transfer functions, right? So again, we will go through a Q&A if you have any questions, okay, before we call these sessions an end. Okay, no. Any more questions? Right, if no questions, you may start to try with the tutorial questions that I've uploaded in the Google Classroom. Okay, I think there are 3 or 4 questions, okay, related to translational and rotational systems. Okay, you just try it, okay, and then we would have tutorial sessions. I would give you 1 week. Okay, actually my planning is you have 1 week time to go through the tutorial before we enter the tutorial sessions. So because of the holiday last week, then we have this disturbed session. So again, because of that, tomorrow we will not have these tutorial sessions. Okay, we will do it a week later, right, which is the following Friday, right? So you have 1 week to check, okay, to understand before we discuss in the tutorial next sessions, right? So if no, then we will end these sessions. Stay safe, everyone, and if you are not clear, you can always ask again during tutorial sessions, right? So stay safe, everyone. See you again. Bye.